Hello everyone and welcome to the lecture series on CFD pre-processing. In this series, we'll look at ANSYS ICEMCFD, a pre-processing software supplied by ANSYS Inc. ICMCFD has a vast capabilities including mesh generation for CFD as well as structural solvers. It also has large number of post-processing functions. In this lecture series, we'll focus only on its CFD meshing capabilities. To activate only CFD version and its necessary UI components, you need to do appropriate product settings. To do so, go to Settings menu and Product submenu. Activate CFD version along with blocking, apply and restart the application. This is the outline of our discussion today. First, we'll look at overall tasks involved in pre-processing. Then, we'll look at various cell shapes supported by standard CFD solvers like ANSYS Fluent or ANSYS CFX. We'll also look at various grid generation methods. Later in the lecture, we'll discuss more about various operations done in ICMCFD. Then we'll look at different components of UI and their functions. We'll also look at various files associated with ICMCFD and their data content. Work and data flow in ICMCFD depends on meshing strategy selected. At the end of the lecture, we'll discuss general as well as a specific workflow in a typical meshing requirement. After understanding the concepts in this lecture, you should be comfortable with UI of ICMCFD and overall workflow. You should be able to navigate through the software and locate the necessary functions. Before going into the details of ICMCFD UI, let's discuss more about what is pre-processing. From our CFD fundamental lectures, you might have understood that computational fluid dynamics is a method of solving governing equations using numerical methods like finite difference, finite element, or finite volume. In all these methods, the governing equations, either in a differential form or an integral form, are discretized and rewritten at either a point or for an element or for a control volume. Control volume is also called as cell in CFD community. As the equations are written and solved in discretized form, the domain or the geometry in which the equations are going to be solved also needs to be discretized. So to facilitate the solution of governing equations using numerical methods, we need to give following domain inputs to the solver. The first input is shape and size of the domain. This defines the region in which the equations will be solved. We then need to discretize the domain as it will be given to the solver solving governing equations in discretized form. To identify the domain boundaries during solver setup, we need to give appropriate boundary taggings. This is also called as setting up boundary conditions. The mesh with all this information is then needs to be written in the file or format understood by a selected solver. If physics of the problem is same, then in CFD analysis, same governing equations are solved. Let's take a simple example. Imagine that you want to find the pressure drop across inlet and outlet of a duct and a control valve. In both the cases, we need to solve for an incompressible flow of water. In this case, solution of continuity equation, three momentum equations, and turbulence equations is required. But if you look at the end results, you can easily notice that the flow feature is different in duct as that of a control valve. This difference is the result of different boundary conditions used for both the cases. So as to result into a unique solution of governing equations, we need to give unique boundary conditions. The uniqueness of boundary condition is defined by shape, size as well as value of known flow property on the boundary. A typical CFD preprocessing activity involves creating the shape and size of the domain. This is generally supplied through a CAD data. This CAD model is generally created using a CAD software or a geometry modeling features available in ICMCFD. Due to the limited geometry modeling features available in ICMCFD, it is mainly used to create a simple geometries. In case of complex geometries, a standard CAD software is used, which can generate complicated CAD model within a short time. But this comes with its own limitation and requires considerable CAD repair. The next activity is dividing the domain in small parts or subdomains. This process is also referred as mesh generation, grid generation, or domain discretization. There are various grid generation methods. Broadly, they are divided into three main categories, namely structured multi-block meshing, Cartesian meshing, or unstructured meshing method. Once the correct grid is generated, the next activity is putting boundary tags as well as domain tags. The boundary tags involves labeling the surfaces of the domain with labels like inlet, outlet, or a wall. The domain tagging involves labeling the volumes with solid or fluid. All this information is then exported in a correct file format understood by a CFD solver. So, to summarize, the overall pre-processing activity involves geometry modeling, grid generation, boundary taggings, and mesh export. Now let's look at the fundamental definition of grid or a mesh. In overall CFD cycle, mesh generation is the most critical and many times a time consuming process. The simplest definition of mesh or grid generation is that it is the process of dividing the domain in small subdomains. You can imagine that the smaller subdomain is equivalent to a control volume we have used during the derivation of fluid dynamics and heat transfer equations. These small subdomains or volumes are typically referred as cells or elements in CFD community. As discussed before, the requirement of grid generation is mainly due to the method of solving the governing equations. We use numerical methods like FDM, FEM, or FVM to solve the discretized form of equations. This then also demands for discretizing the domain or creating the grid. For any CFD engineer, or to be very specific, for any pre-processing engineer, the grid generation task is divided into two sub-activities. The first activity involves dividing the surfaces or boundaries of the domain into 2D elements like triangle or quadrilaterals. The second task is dividing the volume using shapes like tetrahedral, hexahedral, pyramids, or prisms. It is not necessary to use only one type of cell for meshing complete volume. In many cases, a mesh may include combination of all type of elements. To elaborate more on the definition of a grid, refer to the figure on right hand side. In this case, the domain of our interest in which we want to solve the governing equations is the region between two concentric circles. For creating the grid, we have selected a simple triangular shape for subdomain or a cell. After completion of grid generation process, the domain is filled with set of triangles. The generated grid should follow some governing laws and should have some critical properties. The first important property is that all the triangles should collectively fill the complete domain and there should not be any unmeshed region in the domain of interest. The second property is that none of the triangles should intersect with each other. All the triangles should be connected to its neighbors at their vertices. If you closely observe the grid generated for the region between two concentric circles, you can notice that it follows all these critical properties. Apart from these properties, in order to get good quality solution, we should also look at other properties of a mesh. This includes quality of a mesh, distribution of mesh nodes and its growth ratio, and many more. Later in the lecture series, we'll discuss more about different quality criteria one should check before submitting it for the solver. There are many governing factors which decides the shape of the cell one should select for meshing. The most important factor is that the selected shape should be supported by the solver. During the solution of governing equation, solver needs to do some mathematical calculations over every cell. This includes calculation of properties like volume of a cell, surface area of a cell face, as well as face normals. This is possible only when solver implementation has specific functions for such mathematical calculations. So before selecting any cell type, one should always check the types of cells supported by intended CFD solver. ANSYS Fluent has support for wide variety of shapes. It supports triangles or quadrilateral elements in 2D. Many times these are referred as tri or quad elements. In 3D, it has support for tetrahedral, hexahedral, pyramid and prism elements. In general, tetrahedral and hexahedral elements are referred as tet and hex elements. A typical meshing activity involves generation of all type of elements. ANSYS Fluent also supports non-conformal interfaces between two meshed regions. We'll discuss about generation and treatment of non-conformal mesh later in the course. There are many grid generation methods, and advancement in various algorithms has enabled creation of high quality grid within small amount of time. All the methods are broadly divided into three categories, namely Cartesian methods, structured methods, and unstructured methods. The structured method is further divided into monoblock and multiblock method. There are large number of unstructured grid generation algorithms, but the most popular one includes octree based methods, advancing front methods, and Delaunay triangulation methods. Generally, unstructured grid generation method results into tri-surface mesh and Tate volume mesh. There are certain unstructured methods which can also generate chord as well as hex elements. Hybrid mesh generation process involves using more than one meshing method for generating mesh for entire geometry. Typically, a simple region is meshed with hex elements using multi-block approach, and a complicated region is meshed with Tate elements using unstructured approach. The two regions are then either merged with a layer of pyramids or combined with a non-conformal interfaces. Till now, in the lecture, we have seen basics of pre-processing. Now let's discuss more about ANSYS ICEMCFD, a pre-processing software. ANSYS ICEMCFD is a complete and stand-alone pre-processing tool for CFD. The complete word implies that it does all the operations including geometry creation, grid generation, boundary tagging, as well as export grid to various solvers. The standalone word implies that it does not rely on any other software inputs for the process to start or end. There are certain softwares like ANSYS T-Grid which need surface mesh as an input. The typical task in ICMCFD involves geometry related activities, mesh related activities, boundary taggings, and grid export. The geometry activity includes both import and repair or geometry creation within ICMCFD. Meshing activity includes creating the mesh using various meshing techniques available in ICMCFD. It also includes either automatic or manual repair of generated grid. The boundary tagging is also done within ICMCFD for easy solution setup. The grid is then exported in various solver formats. So to summarize, activities in ICMCFD involves geometry creation, mesh generation, boundary taggings, and mesh export. Let's have a look at all these activities in detail. The first task in ICMCFD is geometry creation, which defines the shape and size of the domain. Most of the industrial problem involves complex geometries which are either impossible to generate in ICMCFD or consumes lot of time. So, the general practice is to use standard CAD softwares to generate the CAD model. In such cases, depending on the format of a CAD data available, various functions of ICMCFD are used. If the model is available in faceted or triangulated format, using faceted data reader, the data can be imported in ICMCFD. There are various geometry and CAD readers or translators which can import the geometry present in neutral file formats like IGS or STEP. In most of the cases, translation operation causes data loss and asks for CAD repair before meshing. Along with above methods, it is always possible to use direct CAD interfaces to input the geometry in ICMCFD. In case of simple geometry, ICMCFD's geometry modeling capabilities can be utilized to create the model. Various geometry functions available in ICMCFD can also be used for geometry repair in case if it is imported from outside. This is the overall geometry operation done in ICMCFD. We'll get into the details of every operation during our geometry creation lecture. Once the geometry is finalized, it is followed by mesh generation process. Let's have a look at the overall task involved in mesh generation. All the grid generation methods available in ICMCFD are divided into two main categories called patch conformal methods and patch independent methods. We'll get into the details of these methods later in the course, but at this point of time, you can imagine that patch conformal method treats every surface as a patch and creates a grid on its boundary and then on the patch or the surface. In case of a patch independent meshing, more than one surface can be combined in a patch simply by removing in between boundary curve. This greatly simplifies the complicated CAD model for meshing. As mentioned before, all three methods, namely Cartesian based method, unstructured method, and structured multi-block methods, are available in ICMCFD. Using all these methods, a grid is generated and, if necessary, is followed by a mesh repair operation. In case if quality of grid is not good, we can use various mesh edit tools available in ICMCFD. Few of the tools are automatic and few requires manual work. Edit mesh tools are mainly used in a case when unstructured grid generation methods are used. In case of a multi-block structured meshing, the quality of grid is mainly improved at pre-processing level by modifying the block topology or vertex alignment. Edit Mesh also provides other tools like generating the conformal interface between two mesh domains, extruding the boundary mesh in specified direction, transforming or aligning the mesh, and quality checks. So, overall mesh edit operations are used to improve the quality of a grid. Once the correct mesh is generated, it needs to be written in a format understood by a selected CFD solver. The task involves selection of a solver, assigning the boundary types, and exporting the mesh. The available boundary types and mesh format depends on selected solver. So this is the process overview of different activities done in ICMCFD. UI of ICMCFD is divided into 6 components. The first component is a main menu located at the top of the UI. It has File, Edit, View, Info, and Settings menu. It also has a Help menu which gives access to various help manuals. We'll look at all these menus in detail later in the lecture. Below the main menu, various utility icons are present. These utility icons gives access to most frequently used functions in ICMCFD. To the right of utility icon, various function tabs are present. These function tabs gives access to different functions used in ICMCFD. The number of function tabs present depends on the product settings. In case if CFD version is activated with blocking, you should see only function tab related to geometry, mesh, blocking, edit mesh, and output. The current UI shows other function tabs also. This is because the default version of ICMCFD is currently active. To activate only a CFD version with blocking, go to Settings, Products, activate CFD version, deactivate post processing and card 3D also, activate ICMCFD under a GUI style, apply, and restart the software. Now, if you see, the necessary CFD function tabs are available. We'll look at the details of all the functions present under each function tab later in the respective lectures. The data entry zone is present below to the utility icons. The content of the data entry zone depends on the function selected. All the forms which are opened in a data entry zone will ask for few text inputs, it will have few drop down list, it will also ask for numerical values. It contains the command buttons like apply, OK or dismiss. We'll see the content of every form in detail during the respective function usage. Model tree is present below DEZ area. The components of the model tree depends on the data present in current project. In case if only geometry data is present, it will have a tree related to geometry and a tree related to parts. You can always expand the subcomponents of the tree by clicking the plus sign. We'll see the details of every component of the model tree later in the lecture. Major portion of ICMCFD's UI is covered by a graphics window. Graphics window displays various states of the model. You can always use the mouse button to operate on the model displayed in a graphics window. The display triad is present at the right bottom corner of graphics window. It contains XYZ axis and a central sphere. You can always click on one particular axis symbol to orient the model perpendicular to that axis. You can also click on the central sphere to get the isometric view of a model displayed in a graphics window. The background of the graphics window can be changed by using settings, background style, and you can give either a gradient or a solid color. Let me give a white solid color as a background. You can also change the size of the graphics window by click and drag on the vertical as well as horizontal gray lines. Similarly, you can also change the area of the model tree, the area of the message window by clicking and dragging on the respective gray lines. The message window is present at the bottom of UI, which displays various messages given by ICMCFD. It also shows the necessary information in case if any query is asked to ICMCFD. In case of any error or failure of a particular operation, the diagnostic message will be displayed in the message window. These are various components of ICMCFD UI. Please take a pause at this moment and browse through the UI and get familiar with various components. You can always use the tooltips which you can access by simply pointing the mouse on respective functions. The dynamically linked help is available in every form opened in a DEZ area. If you click on the question mark on the top right hand corner, it will directly open the respective help and give you the necessary information. Before going into the details of each component of UI, let's have a look at files associated with ICMCFD and its content. There are various files associated with one ICMCFD project. Rather than storing all information in one file, ICMCFD uses different files to store different information. This multi-file structure gives better and faster control on data input-output and its usage. All the files are stored in one project directory. The best practice is to create a project directory and select that as your working directory. You can do this by using Change Working Directory submenu provided in File menu. Please go and create a project directory and set it as your working directory. This working directory is also referred as a project directory. The first file associated with ICMCFD is a project file with an extension .prj. This file contains various project settings and links to other associated files. During project execution, one can select to save all project files or to save specific file. In case if a project file is saved, all associated files are automatically saved. At the later stage, if a project file is opened, all associated files will be opened provided that they are present in same working directory. The next file is a geometry file with an extension .tin. Tin stands for tetra inputs. The main content of this file is the geometry data. It also has information about material points, part association, global as well as local mesh size provided on the geometrical entities. The mesh information is saved in .uns file. UNS stands for unstructured mesh. This file gets generated when unstructured mesh is created or when the block mesh is projected on the geometry. The .blk file contains the block topology. This file gets generated only in case if multi-block structured mesh is generated. There is a great advantage of giving independent control on this file. This allows us to use same blocking file on various geometries with same topology. This helps us during parametric study where a small change in geometry is done to study its effect on flow physics. The .fbc file contains boundary condition information. This includes tags as well as type of boundary conditions given. The type of boundary condition can be assigned using boundary condition function provided in output function tab. The .rpl file is a replace script file which is used to store script or commands for ICMCFD. These are various files associated with ICMCFD project.